Hello everyone, welcome to the lecture on computer architecture and organization. So today we are going to see about unit 2, that is computer arithmetic. So before getting into unit 2, let us recap unit 1, what are all the things we studied. So we studied evolution, the growth of the computer technology, the classes of computing applications. Then we discussed about the performance of CPU on the basis of CPU time. And next thing we discussed something on instructions, that is about instruction set and addressing modes. And in this unit we are going to study about computer arithmetic. So we all know what is arithmetic. Arithmetic is nothing but the mathematical numbers and the operations we are performing on the mathematical numbers that take the term arithmetic. So if you see this quote, that is, the numerical precision is the very soul to science. So this quote speaks about this unit. So if you want to represent a number, the precision is matter. So precision in the sense we want to represent the number as much as accurate as possible. So the first point in this slide is integers can be represented in either binary or decimal form. So integers always can be represented only in binary, that is ones and zeros, or the decimal number that varied from 0 to 9. So we played only with the integers. So if you want to represent a number in the computer memory, then the number may be of any form. It may be of any real number, it may be of a fixed number, it may be an integer, or it may be a fraction. So the fraction may be of two parts. One is two types. One is that of this fixed point operations, and another one is floating point representation. So if you want to represent a number in fraction, and if you want to represent other real numbers, how can we represent in computer memory? How can we store the result of an operation in a computer memory? So we are going to see about this in the following lectures. So the next point is what happens if an operation creates a number bigger than can be represented. So we are performing an operation. So we are adding two 4-bit. So if an operation that creates a number, it is of 5 bit, then definitely we are in need of one more bit. So we want to make the space of the computer memory very much large. Similarly, if the result of an operation is infinity, then that needs to be informed by the computer architecture. As well as if we want to represent a number that is very bigger that cannot be represented, say for example it may take up to 300 digits of length, then how will we represent that in computer memory? So that's the question here. And the next thing is that how does hardware really multiply or divide numbers? So if we are doing the multiplication and division, then how does hardware accepts? So that is the mystery here. So we want to, it is like a riddle. We want to open all these answers for this riddle. So the following slides shows the answer for all the query that we are speaking. So this is addition and subtraction. So in the basic classes we have studied about addition and subtraction. So here we are adding two positive numbers, that is adding plus 6 to plus 7, both are in base 10, that is both are decimal number. So for 7 we are representing in the binary as 0, 1, 1 and 1. Since MIPS instructions are of 32 bit and it contains 32 registers. So keep it in mind, MIPS instruction set, it is of 32 registers and each register can hold 32 bit. So we are saving this operation or storing this number in binary form in 32 bit. So it is 0, 1, 1, and we are extending the remaining bits with a more significant bit in the last part, in the last 4-digit part. Okay. So in the last 4 digit, the MSB is 4. So we are extending this 0 with the remaining of the bits. Similarly, if you see 6 to the base 10, so the 6 to the base 10 is represented as 0, 1, 1, 0 to the base 2. So 0, 1, 1, 0, the most significant bit is 0 and we are extending this more significant bit to the remaining part of the bits. So if we add together, 1 plus 0 is 1, 1 plus 1 is 10, and here we are having a carry 1, and 1 plus 1 plus 1, which is equal to 11. So 1, again we are having a carry 1, and 1 we are having here. So the remaining part, if we add all, gives the bits as 0. So the 1101 in decimal, it is equal to 13 to the base 10. Okay. So that addition is very simple. If we come for subtraction, we are going to subtract a number, that is 6 to the base 10 from 7 to the base 10. It can be done via 2's complement. You can directly do the subtraction by the borrow method. Whereas if you are not very comfortable with the borrow method, then we go for 2's complement. So what we should do is that we need to do this, we are going to subtract number 6 to the base 10. So which number we are going to subtract? So that number we need to represent that in 2's complement form. So in 1's complement to the base 10, the 1's complement of 6 to the base 10 is 1, 0, 0, 1, which means that 6 is binary form is 0, 1, 1, 0. So I have toggled all the zeros to ones and all the ones to zeros for 1's complement. For 2's complement, I need to add 1 to the least significant bit. So 1 plus 1 is 10. So it is 0, again 1, again it is 1. Then I am doing this 1, 0, 1, 0. So I have been added this 1, 0, 1, 0 here, and I have to negate all the zeros to 1. Okay, so all the zeros are negated to 1. So since this is negated, I have represented this number in red color. So now the addition goes like this. So 1 plus 0 is 1. 1 plus 1 is 10, 0. Again here's a carry. 1 plus 1 is 10. Again it is 1. It is carry. So if you do like this, so the carry travels and it takes place here. Okay. So about this, let us see. Now I have not represented this one here. Let us speak later about this. Okay. So this is a 2's complement calculation. So 2's complement calculation is 1's complement plus we are adding the 1 to least significant bit. That is represented here. And keep it in mind that subtraction is addition's tricky part. So if you keep remember all these things, then you will easily do the subtraction in 2's complement form. Now we are going to see about detecting the overflows. So what is overflow? The overflow takes different meaning here. It is not something that we are adding the 2 whole bits and we are getting the result as 5 bits. It is not like that. Overflow has an impact on the result. Okay, so it completely changes the result. It completely changes the look of the result. So what is overflow in the sense? Let us discuss. So take the decimal a, which can be represented as 1, 0, 1, 0. Okay. So now I am going to add this b with a. So b with a, b is nothing but 1, 0, 1, 1. So now I am going to add these 2. Okay. We are adding this 2. So 0 plus 1 is 1. And 1 plus 1 is 10, so 0, again it is 1, and again I am carrying down, it is 1, 1 plus 1 is 10, now I want to represent this 1 here, okay. So this is the most significant bit here. So what is the beauty of the MIPS architecture is that the most significant bit fills all the remaining bits of the 32-bit register. So this 1 will be filled in all the remaining parts of the register. So if you have a look, we have added the 2 positive numbers. So the result should be in positive. So imagine this is the sign bit. Okay, we are having a sign flag in the register. So if we have a sign flag, so what it should be? It should be actually 0, but here it is 1, since because of the carry. Okay, so instead of the positive result, it poses like a negative number. We have added these 2 bits, that is 2 positive number, and the result we are getting is the same number, that is 10101. It is the actual result, but since because this MIPS extend the remaining bits of the register, with the most significant bit, this result poses like a negative result. Actually, positive plus positive should come as a positive result, but it poses like a negative result. Okay, so now this is termed as overflow here. Okay, so if you are a negative number, the most significant digit is the most significant bit is 1. If it is a positive number, the most significant bit is 0, or the sign bit is 1 for negative number and 0 for positive number. Okay, so now see here, this is the operation and this is operand A. We are performing the operation on two operands, that is operand A and operand B, and this indicates the result indication overflow. So see the first row, that is A plus B. We are performing two positive number addition. So operand A is greater than or equal to 0. This is positive. Operand B is greater than or equal to 0. That is positive. But result indication overflow. But result poses like a negative number. So that is less than 0. Then we term this as an overflow. Okay. Overflow in the sense the carry affects the sign bit and the sign bit changes the result. So second thing, A plus B. Here the operand A is less than 0 and operand B is less than 0, but result seems like greater than or equal to 0. So positive. So this is an overflow. And if you see the operation on these two, that is A minus B, we are subtracting B from A. So operand A is greater than or equal to 0. Operand B is less than 0. Okay. So but the result actually if we want to get is greater than 0, but we are getting, it seems like less than 0. And see this, A minus B, here operand A is less than 0, operand B is greater than or equal to 0, but the result indicating the overflow is that is greater than or equal to 0. Actually it should be less than 0. Okay, so this is overflow. Hope you have understood. So effects of overflow, joy can overflow, but numbers cannot. Okay. So effects of overflow in the sense it creates something inside the program, it affects the result, it is the worst part in the program, and it affects the flow of that program. So if it affects the flow of that program, then we call this as an exception or interrupt. Okay. So if an exception or interrupt occurs, the control jumps to predefined address for exception and the interrupted address is saved for possible resumption. So these things, there are so many steps. If overflow happens, then the program needs to perform. So if you see about the performance, it includes the clock cycle, it based the time of the processor. So overflow affects something. And don't always want to cause exception or overflow. So these add I, that is immediate operation, subtraction causes exceptions on overflow, but add unsigned and add immediate unsigned and subtraction unsigned do not cause exceptions on overflow. So unsigned numbers doesn't cause anything on overflow, but the signed integers or signed floating point operations causes some exceptions on overflow. Okay. So what is an interrupt? Interrupt is nothing but an exception which we have already talked about. So exception, it is also called as an interrupt. On many computers, it is nothing but an unscheduled event that disturbs the program execution and is used to detect the overflow. Okay. Usually the interrupt that comes outside of the processor. It doesn't happen inside the processor, it comes outside of the processor. Now here we are going to see about the MIPS instructions for arithmetic. So if you see about this arithmetic, instructions on arithmetic, integer arithmetic operations on full word, because integer arithmetic operations takes place on full word in the sense it is on 32-bit. But data transfer operations, it takes for bytes and halves. Okay. If you see the instructions here, you will understand. Load with LBU, LHU. Okay. So this is one BU and one HU. So one BU is 1 byte unsigned and 1 half unsigned. Then arithmetic with add, sub, multi and division. Then store using SB and SH. Again load with 1D and 1H. Arithmetic with add, sub, multi, division. Then store using SB and SH. And third is load with 1 byte 1 half and arithmetic with add, sub, multi and div. These all things holds. But using AND to mask the result to 8 or 6 bits after each operation, then store using SB and SH. So this is and operation. It is nothing but a pattern that sets all the bits to 0. So we can use that pattern in order to mask the result to 8 or 6 bits after each operation. Okay. So and used for masking operations. And this is our overflow. No conditional branch instruction to deduct overflow. This is the important point in next instruction. There is no direct instruction. There is no conditional branch instructions to deduct the overflow. So what we need to do is that we need to go through the sequence of instructions to deduct this overflow. So what about, so this is the sequence of instructions. First is add unsigned. We are adding two unsigned numbers and we are keeping the two operands in $T1 register and $T2 register. Operand 1 is in T1 and operand B is in T2. So now we are adding and the sum is in $T0. Okay. So now it doesn't affect anything. Addition, that just do the addition. The machine does the addition and it plays the register. Content in register $T0. Now the next step is XOR. So XOR $T3 comma $T1 comma $T2. So the XOR operation takes place. What this does is that it negates the register, that is $T3, if the two signs of the register, the content in the registers differ. Say for example, if $T1 is positive and $T2 is negative, then $T3 that will be, see here, in $T3 register, it will be -1 if signs differ. That is the important matter. In $3 it will be of -1. Okay. So now this is SLT, that is set on less than $T3 register comma $T3 comma $0. So what this is that set on less than, it just compares this dollar content in the $3 with $0. So what is here in $3T? It is -1, $0 it is 0. So -1 is less than 0. So if signs differ, then automatically it says $T3 is equal to 1. Okay, because here we want to know whether the number is in positive, whether the content of the register $T3 in positive or negative. In order to check that, we are using this instruction, that is set on less than. So if it is equal to 1, then the signs differ. So now we are having $T3 is equal to 1. And now next instruction is branch non-equal. So if it is not equal, $T3 we are having 1 and $0. So these two registers will be compared. Here it is 1, it is 0. So both are not equal. If it is not equal, then go for no overflow operation. The program sequence comes to no overflow operation. Now it is checking for the overflow condition. XOR operation, what is the use of XOR operation? If both the signs differ, then it sets the register $T3 to -1. So now, in order to check the overflow, it compares the sum sign as well as the operand sign. So if the sum sign is equal to operand sign, if both differs, then it sets to negative. So here sum sign is equal to operand sign. Operand in the sense we are using $T1 register here. So you must understand why we haven't used $T2. If you come for this previous slide, yes, see here. So if you come for this one, A minus B, we are speaking about both checking the signs of the both operand. Here operand A is greater than or 0 and operand B is less than 0. The result is opposite to that of this operand A, which is in register $T1 as per the algorithm. Here A minus B, operand A is less than 0 and operand B is greater than 0, but the result indicating the overflow is opposite to that of this operand A, that is greater than or equal to 0. So only we have compared in this algorithm this $T1 register. So if both differ, the sum sign and operand sign differ, definitely it negates. Second step, SLT, that is set on less than, it compares $T3 with 0. Definitely it is not equal, so it sets $T3 to 1. Now again compares branch not equal $T3 $0. If $T3, here $T3 we are having 1 and it is 0. So if both not 0, then both are not equal, then it goes to overflow. So this is the this is the sequence of instructions that is executed by MIPS in order to detect the overflow. And this is for unsigned operation. So unsigned, it is add u $t0 $t1 $t2. It sets $t0, the sum, it keeps the sum in $t0 register. NOR operation, what is the use of this NOR operation? XOR just compares the sign and negates if both are signed equal. NOR operation is just does the NOT operation of the register mentioned here. So $t3 will include the NOT of $t1 content. Okay. Now it compares set on less than unsigned. So this U stands for unsigned integers. So it compares the registers, both the registers, and it sets the result. Now it checks branch not equal $t3 $0 overflow. So if both not equal, then it goes to overflow. This is for unsigned integers. Okay. So this is hardware's dilemma. So it is a very important point here. This is taken from the text that is Computer Organization and Design by David A. Patterson and John Alesi. So what is the problem is that MIPS includes a register called the exception program counter to contain the address of the instruction that caused the exception. But the instruction moved from system control, that is MFC0. Okay. So MFC0 is used to copy this exception program counter. So exception program counter. Okay. So this MFC instruction is used to copy the EPC into a general purpose register, so that MIPS software has the option of returning to the offending instruction via a jump register instruction. So what is the concept is that it just it first holds it includes a register to contain the address of the instruction that caused the exception. So that is first stored in EPC, that is exception program counter. But jump instruction cannot come to EPC directly. So what does is that the EPC transfers the content to another general purpose register via the instruction that is MFC0. Okay, and then and via the jump instruction we can jump to the address that it comes to the instruction that caused the exception here. Okay, so the first point is that the interesting question is that since you must first transfer EPC to a register to use with jump register, how can jump register return to the interrupted code and restore the original values of all the registers? Either you restore the old registers first, thereby destroying your return address from EPC, which you placed in a register for use in jump register, or you restore all the registers but the one with the return address so that you can jump. Meaning an exception would result in changing that one register at any time during program execution. Neither option is satisfactory. Okay, so both the options are not satisfactory because we need to refresh all the registers either first, or we need to refresh the register at the running of the program. So neither will disturb either option will disturb the program. So in order to rescue the hardware from this dilemma, so hardware has a dilemma, which register I need to refresh first. So it has a dilemma. So MIPS programmers agree to reserve registers $K0 and $K1 for the operating system. So these registers are not restored on exceptions, just as the MIPS compilers avoid using register $80 so that the assembler can use it as a temporary register. So this compilers also abstain from using registers $K0 and $K1 to make them available for the operating system. Exception routines place the return address in one of these registers and then use jump register to restore the instruction address. So thank you for watching. Continue watching the remaining lectures. Thank you for now.